So we're going to talk about GD&T introduction. GD&T stands for Geometric Dimension and Tolerancing. It is a new engineering language for you. It uses symbols to clearly communicate design requirements. This is stuff you'll see on the mechanical drawings or the blueprints for your parts that you're manufacturing. Some benefits would include this is a standard deal. So internationally, people are going to understand this. People that are working on different parts. This reduces your drawing assumptions, clearly communicates something called a datum, which we'll talk about in a few minutes. It allows for flexible tolerance zone shapes and fit and function based tolerancing. It also allows for additional tolerances or bonus tolerances. So for what we're concerned with, we're really concerned with international understanding and reducing assumptions here. Tolerances. Tolerances is the basic how far from the actual dimension can a part be and still be acceptable. So the actual dimension is the size of it once it's made. The nominal dimension is the one that's on the drawing. And some benefits or tolerances are there's faster production, reliable part operation, so the pieces will fit the way they're supposed to, reduce cost. If you can make something with a little bit smaller, or excuse me, a little bit larger tolerance, it'll take less machining time and cost you less money. Consistent quality, you want consistently with things you produce. They're given in terms of a plus or minus symbol. This is traditionally the way you'd see a tolerance shown on a mechanical drawing. They're used for simple dimensions such as length and diameter. So, a plus or minus a few thousandths of a diameter or a few thousandths of a length, a width or a thickness. They do not control location, orientation, or complex shapes. So there's some stuff that tolerances don't do very well. It's often not clear how to establish the datum. So, okay, this tolerance is plus or minus 5 thousandths, but from where? Where do I start my measurement? That's your datum. It's a theoretical axis or point or plane from which all the other features are measured. So this would be like where you would start your tape measure if you were measuring with a tape measure, where your 0 point would be on your micrometer or your caliper. This is what they look like. This is a picture of a few different datums. You can see most of them here are labeled A. These are axis planes right here where the mouse is moving around. They're all labeled A. You can see there's a little flag here. As you get into more and more datums, this would be an axis datum here. As you get into more and more datums, such as A, B, and C, they're referenced in the order of preference. So I would measure from A first, and then B would be my second datum, and C would be my third datum. Every feature needs at least one datum, and it must have a linear value associated with it. So there's got to be a number there. The feature control frame. This is what you're going to see on your plans. So you may have seen this before. This may be the first time you're seeing this. It's a box with a bunch of weird looking symbols and numbers in them. Well, this is kind of what they mean and what they do. It's read from left to right. The first box is your geometric characteristic, which we'll talk about in a minute. Your tolerance zone shape. So this would be a diameter tolerance. Your tolerance size is 0.25. Your material modifier, and your datum references. So A first, B second, C third. Standard symbols. This right here, this geometric characteristic is a standard symbol. This right here stands for position. Here are the standard symbols. There are 14 of them, and they are in 5 different groups. Form controls, orientation controls, profile controls, location controls, and runout controls. So without going really crazy into this, your most common ones that you're going to see is you're going to see position a lot, because that's what gives you the location of where something is. So the position of a hole or the position of a notch or something like that. So the form controls, they only reference a feature, they don't reference a datum. So a feature would be anything like a hole or a taper or something like this that you would be machining on a part. They only reference that feature. Your orientation controls, parallelism, perpendicularity, and angularity. This means parallel. This means perpendicular or 90-degree angle. Everything else is, every other angle is uses the angularity symbol with it. Profile controls, profile of a line or profile of a surface. The symbols there. Runout, circular runout would be for a part of something that was round or cylindrical, and the total runout would be the entire part. So you would measure the entire part and check for something called runout, which is the amount that the piece has basically wobbled or bent due to machining. Like I said, location controls, position is your most common. You don't see concentricity and symmetry a whole lot, but there they are in case you do see them. Additional terms and rules. This additional terms and rules, let me back up, is where you would see for your material modifier. So this is your additional terms and rules. MMC, maximum material condition, LMC, least material condition, regardless of feature size, RFS, bonus tolerance, and rule number 1. So these are additional things other than the 14 standard symbols. Here it is in the control feature, or excuse me, in the control, here it is in the feature control frame rather. There it is right there, that M, that's your that stands for MMC, which if you look back is maximum material condition. What that tells me is that that is the maximum amount of material I can have. Maximum is the most commonly used material modifier. If a tolerance does not need to be tagged to a particular feature, like a general tolerance that's on your drawing, assume the tolerance is constant. So say for example you're given a 5,000th tolerance on your drawing and it's not specifically listed on the within the GD&T, then we just call that regardless of feature size. And there's no symbol for that. That's just kind of an assumption that we make and an overlying rule that goes with this. Here is MMC and LMC meanings. Maximum material condition, least material condition. The maximum material that you can leave after machining, the least amount of material you can leave after machining. For a hole, the smallest hole is made, which would leave you with the maximum amount of material. The largest hole for the LMC side would mean you have removed the most amount of the material. For a shaft, the thickest acceptable shaft, and for the LMC would be the thinnest acceptable shaft. And you'll understand that in a second. I'm going to show you another picture. Bonus tolerance permits the maximum use of tolerance while keeping the fit and function of the part intact. So that would be using the maximum amount of tolerance or least amount of tolerance that you could possibly get away with while this piece still fits together. So rule 1, we talked about back here, LMC and MMC. This is where it comes into play a little bit here with rule 1. A shaft must be able to fit inside the hole, which is as deep as the shaft length. So if you look on the drawing, what we're talking about here is this shaft is MMC is 0.874. This hole, its LMC is 0.875 and its MMC is 0.880. So its MMC is 0.880. So what this means is this shaft, this little pin that fits in there, can bend a little bit just so long as it remains within the 0.880 spacing. Okay, so as long as this, if it's bent, fits in that hole, we're good. Same thing for a hole, a bore. Okay, so here's the bore. It's 20 plus or minus 100 thou. So we have 20.1. Anything that's in here, so even if it's a little wavy, maybe your tool marks made, your lathe tool made some gouges into it. As long as it fits in there, it's good. And here it is again with kind of like a hot dog or a banana bent shaped piece. So as long as the piece fits in the hole within its maximum allowable tolerance, we're good. Holes in GD&T. This is where we've seen this before. We've done this a little bit. We've got a couple of different symbols that they use to specify holes. The diameter symbol, the counterbore or spot face symbol, countersink, which is this little arrow, and then the depth or how deep something goes symbol. So over here on this hole note, the first thing is how many times it's repeated. Then we have a diameter symbol. The diameter is 8. Through all is the length of the feature. So it's telling me it's just going, I'm going to cut a 8 centimeter or 8 millimeter hole all the way through. And then I'm going to do a counterbore with a diameter of 13.5 to a depth of 8.5 millimeters. Okay, so that's how you would read that, and that's how you would, that's what all that means. And here we go, is another example of a hole note. There's a blind hole, which doesn't go all the way through. It only goes 0.75 deep, and then a 0.38 diameter counterbore that's drilled 0.25 deep. And you look down here, you can see from this view that there's actually, like, you can see 2 circles in there. One is the first circle, or the first hole, that only goes 0.75 deep, and one is the counterbore, or the larger hole, that goes 0.25 deep. So that's it for now. I will put some other pictures and references up for you to check out. We don't want you to memorize all of these symbols. Let me get back to, you don't need to memorize all these. You probably know what position is. Okay, you might want to know what perpendicular is, maybe straightness, circularity, something like that. But you don't need to memorize what all of these things are and what they mean and what they do. Just need to be able to, let me scroll quick here. This hole notes is really, really important for the macroic stuff, and I would say study this, and we're pretty good.